Welcome to week 9 live session of molecular spectroscopy of physical chemist perspective. I am Arko Prabhu Chaudhary, PMRF at Department of Chemistry, IIT Bombay. So I am going to discuss today the normal modes of vibration and how can we determine the several normal modes of vibration using the symmetry elements in a polyatomic molecules. So this is actually the recapitulation of this is going to be the recapitulation of Professor Anindya Datta's lectures on week 8 materials where he has discussed these things, and today along with that we will solve week 8 assignment problem, and we are going to solve a few specifically he a few two means one is obviously a water and another is PTCl6. With that platinum salt, octahedral salt, we will try to determine the uh, normal modes of vibration of that particular molecule. So before starting that, let us recapitulate a few things about the great orthogonality theorem, which is going to be a very handy expression for this particular live session. Um, the what great orthogonality theorem tells us is actually gives us the relationship between two matrix element of transformation matrix of symmetry operation. Specifically, if I tell you here what are the things, this gives us a summation of sum over all the symmetry operation, and then there is gamma I r mn, that is the mnth element of a transformation matrix of symmetry operation R in the ith irreducible representation. Similarly, what is gamma j r m dash n dash, that is a m dash n dash element of a transformational matrix of symmetry operation R, same symmetry operation in the jth irreducible representation. But we have to take a complex conjugate of this, and if we multiply this with gamma I r mn and sum over all the operations, symmetry operations, we are going to get h by root over li lj, where h is the order of that point group which the molecule belongs to, and what is h also is the total number of symmetry operation, you can say, and li and lj are the dimensionality of this irreducible representations. And then it have to be multiplied by some delta functions, like not delta functions, this is chronicle delta, which is delta ij, delta m dash, delta n dash. What does this means? The delta ij dash is actually, ij is going to be 1 when I is equals to j, else for any other value of I and j where they are not equal, then it is going to be 0. Similarly, delta m dash will be 1 when m is m dash, else 0. Delta n dash will be 1 when n equals to n dash, or else it will be 0 where n not equals to n dash. Now, with this great orthogonality theorem, we have not shown you the exact derivation of this great orthogonality theorem, but you can always go back to NPTEL course symmetry and group theory taken by Professor Anindya Datta himself. I think this course is available freely on YouTube. You can also check it there. So a good amount of lectures have been provided to you, who also there to behind the derivation of this great orthogonality theorem, which uh, most of us don't know how this actually comes. We take it axiomatically, but for this course we are going to take this axiomatically, and from there some working rules are given to construct the character tables. Few of these rules are that we had one question, that how many irreducible representation is possible for a particular point group. It is going to be equals to the number of classes or the number of equivalent symmetry operations. Then another thing is that your character of the identity operation is going to be give you the dimensionality of that irreducible representation. Again, a sum of the square of the dimensionality of a particular irreducible representation is going to give you the order of that point group, and sum over all the operation over the same of the same symmetry operation are character of that same symmetry operation. If you take a square of that, you are going to get again your order of this point group, and the ultimate is that sum over r character of a symmetry operation multiplied by character of the same symmetry operation but from a different uh, uh, different irreducible representation is always going to give you 0. Why? Because delta ij, you already know that I and j are different, that is why you are going to get 0 there. So we have actually discussed the in the previous session we have discussed actually how these fourth and fifth uh, equation have been constructed from this great orthogonality theorem. You can always we can always recapitulate, but you have to remember. So we will not do that in this session. I have just keep it here for your reference. You can always pause the video and check it, but the main thing is that we are going to use this uh, formula, which is sum over r character of a symmetry operation, square of a character of a symmetry operation is always going to give you the order of the matrix, order of the point, and obviously another equation we are going to use, that this fifth one, where it is talking about the orthonormality of the characters of different irreducible representations. We have also discussed in the last session that what is going to be the Mulliken nomenclature for a 1D irreducible representation. It is all the name, it will start with A or B depending on the uh, um, symmetric nature of this irreducible character, or symmetric nature of the character of uh, C2 or the main principal axis, the rotational axis. As you can see, for a C2b point group we have actually here 4 symmetry operation and 4 classes, and that's why we have 4 irreducible representation, the first one being the totally symmetric one, and in all the cases. And after this character table, at this part you can see the basis functions are there. So this first is x, y, z, and then as you can see it is the quadratic terms, quadratic basis like z square, x square, y square, x y, x c, y z, how they transform or what is the symmetry is species, and that can be, we can understand from this character table also. Now what Mulliken symbol tells us, that one second, I guess some something in the to stay in the call, yes, and let us yeah. So for a when how do we do the Mulliken nomenclature of this? Now for a 1D irreducible representation, it is always going to be A or B. Depend what does it depend on? It would be A or B. It will depend on the symmetry, depend on the character of the principal rotational axis. Here as you can see, C2 is the principal rotational axis, and upon that the irreducible representation is actually symmetric, it is 1, that is why it is going to be A. If it is a -1, that is anti-symmetric with respect to C2 or the main principal axis, then it would have been B. Like the third irreducible representation is B and fourth one is also B. Now the next part will come, it will be A1 or A2. It will depend, this 1 and 2 depends on the next symmetric nature of the next character of the symmetry of next symmetry operation, like here it is sigma v xz. As you can see that it is the first one, the first irreducible representation, which is a totally symmetric one, it is actually symmetric with respect to sigma v. That is why this is called A1, and the second irreducible representation is not symmetric with respect to sigma v, that's why it is A2. Similarly, for other symmetry operations like, excuse me, sorry. So for other symmetry operations like sigma h, which is a molecular plane, if it is symmetric with respect to the molecular plane, that is 1, and then it is going to be a single dash, and if it is going to be if the molecular nomenclature, there will be a double dash if it is antisymmetric to the molecular plane or the sigma h symmetry operation. Again, if your character of a particular irreducible representation is symmetric with respect to your inversion, if there is inversion center there inversion symmetry element is available, then if it is symmetric with respect to that, then we will write G, that is Girardet, and if it is antisymmetric with respect to the center of inversion, then you are going to write it as U, which is Ungerath. Okay, so by like this we will do the nomenclature. Actually, why I have discussed this, because in the week 8 assignment there is going to be there is a problem where we have to find out a nomenclature of a particular irreducible representation. Anyway, you can always find out more say irreducible representation related molecular nomenclature related problems from the internet and try to solve yourself. The more you practice, the more you remember these things. Anyway, the most important formula that we are going to use for this particular today's session is this one, that how many number of times your irreducible representation is going to present in a reducible representation. This particular the expression I am highlighting, let me highlight this one, and so the number of time it will be there is actually 1 by h, that is 1 over the order of the matrix multiplied and sum over all the symmetry operations, and it will sum over all the symmetry operations here, then the character of your particular symmetry operation multiplied by the character of the irreducible representation we are focusing on of that particular symmetry operation. So how did we get it? As you remember that we from great orthogonality theorem tells us this, the sum over R and this thing I will not repeat, but from here we have two working formulas, as I told you, that sum over R character square of the character of a particular of the same from the same irreducible representation of a symmetry operation is going to give you the order of that point group, and this orthonormality expression. From there, actually what we are trying to say, suppose there is some a reducible representation gamma RR is present, we can write it as a linear combination of several irreducible representation, and this AJ is how many number of times this gamma j appear in that reducible representation. Now if I can write it like that, then the character of that reducible representation we can write it like the second line, this blue line, as you can say, character of that reducible representation is going to sum over j aj character of this jth irreducible representation of the symmetry operation R. So now what we will do, that we will, I have done a right multiplication, you can also do a left multiplication, it is not going to be a problem, but if you do a multiplication with chi j r and sum over all the symmetry operation, you are going to see you are actually generating that sum over r, and you are writing again this formula sum over j a j chi j r into chi I r. Just remember this is I, and your reducible is made up of j. Those are different. So you are now particularly focusing on a ith irreducible representation, how many times that is going to come, right? Now what does this, when we break this up, what does this expression actually means is that it is sum over r. Now suppose I am taking j, we will start from j equals to 1. So what is a1 chi 1 r, but it is still chi I r, right? Because we are summing over j, not I. Then similarly the next term comes a2, it is j equals to 2. Then like this it will go on, and it is equals to sum over, at certain point your j is going to be equals to I, right? Then what is that, ai chi I r into chi I r, right? And then again there are multiple terms is going to be there where your j is greater than I for those terms, right? What does this gives us? When, as we know from this second formula, when I is not going to be j, like this first, second and all the terms, most of the terms, then it is going to give me 0, right? This is going to give me an orthonormality from this orthonormal or you can say orthogonal expression, that this is going to give me 0, and this particular, this one term in this expression is going to give me this ai is going to be there, and this summation over r chi I r square, that is your order, right? Order of this point group, and I have written it like this aih. So this term can be replaced by aih. So overall what we got from the right hand side, we have sum over r chi of r into chi I of r, that is going to be equals to ai into h, and from that you can get the value of ai. That a, what is ai? The number of time the ith irreducible representation occurs in the reducible representation. So based on this, actually yesterday I have given not yesterday, in the last session actually I have provided you a 4 question to solve homework problems. Today we will start with that how to break down a reducible representation, these 4. So the question says that deconvolute the following reducible representations into irreducible representation. Irreducible ones represent reducible representation gamma as a sum of irreducible representation. So that is these, what gamma is given, this is your so there are 4 different character tables, 4 different point groups are provided, d2 c3v d2d e and tetrahedral, and for all of these one of each reducible representation is given. So and character table is also given, so we need to deconvolute this reducible representation into the irreducible representation. So we'll do it. Let's start. But before that, let me check one thing first, that if we are properly recording the session. Yes, we are recording. Let us come back. So we'll start from here. So this is our reducible representation. I will just use this color. Reducible representation. D2 character table is given. So for D2, as we can see, there are 4 symmetry operation. Actually identity and 3 different symmetry operation, actually all are rotational axis, but with respect to different coordinates, and there are these linear function rotations, quadratic functions, the cubic functions. These are also I have provided you for your future reference. You can always go back to the Google it, and you will find particular website is there. I currently don't remember the website, but there you can get all the character tables for given point group. But what is the formula we have got? We have got the formula that your AI is going to be 1 over h, your order, then is sum over r chi of r. This is your character of this reducible representation multiplied by character of your irreducible representation, what you are going to look at the same symmetry operation. So there are four irreducible representation is there. So let us start from let us see how many times a is there. Okay, but before doing that, let us see the nomenclature. Always when you get a character table, try to find the molecular nomenclature by yourself, right? So here actually you will see they have written this a of a will be what is the order of this d2 point group. It is 1, that is sum over these characters of this identity operation, as we know from the working principle of the coming from the great orthogonality theorem, that is going to be 4. So your h is 4 here. Then we are, so I will not write the sum over like here, I will erase it and I will. So there are 4 classes also. So what I will do that first I will take the character of the reducible representation and then I will take from the irreducible representation. So 4 multiplied by 1, right? For this irreducible representation we are working on a. Then we are going to write 0 is the next character of c to z and we'll multiply by 1. Then all are actually I won't specifically mention, but all will be 0, right? Because of it is in reducible representation, all the characters are 0. So actually what you are going to see, 1 by 4 over 4, you are going to get 1. So you in your reducible representation a is there one time. What about b1? So here you will see one interesting thing that we during the Mulliken nomenclature, but I was also thinking that what we have told that for a Mulliken nomenclature, your for a one-dimensional irreducible representation, your Mulliken nomenclature will always start from a if your character or your irreducible representation is going to be symmetric with respect to your principal axis, right? But for here you see the second irreducible representation, it is symmetric with respect to c to z, but still it is nomenclature is b1. I am not sure why they have done it. It is possible the nomenclature is set upon C to Y because C, and then again uh, you will say then why it is B2. Then I think there is some mistake here. It should have been A1 and this should have been A2. So I will not change it here. I have just taken it from a particular website. I will show you. I will that would be good, I guess. The particular website is this one, symmetry.jacobs. Here you are going to get all the character tables and all. I will just show you how to do that. Yes. So we are looking at D2, right? So I have taken it from here. Possibly I have made some mistake or they have done this. So maybe we can search other uh, D2 point, not D2H, D2 point group character table, maybe, right? Let us see any other websites. Okay, there also it is A, B1, B2, B3. So I will try to look at why this particular nomenclature is there. I will look it in the, I will study more. But for now, don't get confused. Whatever formula is given to you regarding the molecular nomenclature, follow that. So this might be a particular okay, a peculiar case. I'll look at this and maybe discuss on the next session. It just came to my eye and I just thought to discuss with you. If you have any idea why it is happening, please mention in the comment box, or you can unmute yourself and discuss it. Anyway, so let us get back to our discussion. How many times B1 is going to be there? That is going to be 1 over 4, then 4 into 1, and rest all the things is going to be 0, right? So I will not write it explicitly. Maybe this is the last time, and this is going to be also 1. And I guess you have understood that for the next one also, B2 is also going to be 1 over 4 into 4 other terms is going to be 1, and a B3 is also going to be 1. So what we got is that your gamma reducible representation is actually have a one time, all the representations are there each one time. Okay, I will just highlight the answer. Okay, now let us go back to solve the other three, rest of the three. So here it is a C3b point group. If you remember, ammonia NH3 is a example of a molecule which have a C2 C3b, belong to C3b point group, and the C3b character table is also provided to you. So let us solve it. I'll always start with the formula. The formula is 1 over H over R chi R chi IR. So always remember that in GOT or great orthogonality theorem, it was all about the particular symmetry element or matrix element, to be specific, matrix element of a transformational matrix of the symmetry operation. But in this formula what we are using, actually the character of that uh, transformational matrix. So we are taking some of that diagonal elements, so it's not really the same. So you have to remember, or you have to know that how this formula has been uh, constructed, or how we have arrived to this expression from the great orthogonality theorem. This is not given directly, so we have reached here by some mathematical manipulation, you can say. Now let us see how many times a1 is going to be there. Here e has a dimensionality of 2, right? So you know the molecular nomenclature. If you check this, your molecular nomenclature, you will see that it is fine. So now see how many total number of operation is there. Actually you can see 3 symmetry elements, but actually 3 classes, but you will see the total number of symmetry operation is 1, 2 C3 and 3 sigma b. So actually it is 6. Total number of operation is, I will write it here, total number of symmetry operation. So let us see, a1 is 6. Now what is there, we will multiply 7. This is your reducible representation, so we will multiply 7 into 1, right? Next 1 into 1, should we do it like this? Actually we are going to be in trouble if we do it like this. If you remember, this sum over all the symmetry operation here, you have to remember in this class, actually this is class, so there are actually 2 symmetry operations belong to this particular class, so you should always multiply starting with 2 into character of this reducible representation into character of your irreducible representation. Then you will have 3 symmetry operation in the next class, and we will multiply 3 into minus 1 of character from the reducible representation and plus 1 here. So let us see what did we get. 1 over 6 into 7 plus 2 minus 3, which is 1 over 6 into 6, that is 1. What about the next one? A2 is going to be 1 over 6, again 7 times 1, then 2 times 1 into 1 plus 3 times minus 1 into, which is minus 1. So you are going to get 1 into 6 over 7 plus 2 plus 3, that is 12. So 1 over 6 into 12 is going to give you 2. So why we are doing this problem, even if it looks easy, but it is a good practice to do this, because we are ultimately going to discuss about the normal modes of vibration, how to get the normal modes of vibration, symmetry elements of normal modes of vibration. For that we will particularly require this technique. So 7 into 2 plus 2 into 1 into minus 1, then actually 3 into minus 1 into 0. So this doesn't contribute. So this is 1 into 6 into 7 minus 2. Sorry, actually 14 minus 2 again. Which is 12. So it is also there 2 times. So your gamma reducible is actually, for this particular case, A1 is there 1 time, A2 is there 2 times, and E is there for 2 times. Let me highlight this answer. Okay. Now I will go to the next one. So this is a D2D point group, and the character, there are actually how many, 5 irreducible representation are there, upon which 4 are 1 dimensional and 1 is 2 dimensional. So here also, if you see, it follows the Mulliken nomenclature A1, A2. Why they are named as A1 and A2, you will get to know, right? Here S4 is given a first priority, right? As you can see, and according to that, your nomenclature has been provided. So one, a symmetry nature of it is symmetric with respect to S4. For B1 and B2, they are anti-symmetric with respect to S4, but you can see they are symmetric with respect to C2. Maybe can we have any idea why then, why this is B1? No, not really. Anyway, let us come back. So this is your reducible representation. Your over H summation over R chi of R. Here your order of the point group is see E1, then 2S4, that is 3, 1C2, that is 4, 2C2 dash 6, 2 sigma D, that is 8. Total symmetry operations are 8. So first let us start with A1, right? So 1 over 8, 6 into 1, right? Then 0, I will not write anything. Then minus 6 into 1, then 0 plus 0, I will not. This is easy. If there is the characters are going to be 0 in the reducible representation, this is actually going to be easy for you. As you see, this is 1 over 8 into 0, actually 6 minus 6, that is 0, and there is no A1 in the irreducible representation. This means that. What about A2? 1 over 8, 6 into 1 is going to be there for our, then 0, then what about this, minus 6 into 0.1 again, not 0.1, 1, and this is again going to be 1 over 8 into 0, that is 0. So there is no A2 also. What about B1? 1 over 8, here also it is same, because they are all symmetric with respect to C to Z. So this is also 0. And if you do this, what I believe, it is also going to be 0, right? I am just writing it for your clarity, right? I hope you can also do it by yourself and get this correct. So what I can understand from here is that this two-dimensional irreducible representation is going to be there only. 6 into 2, 12, then 0, then minus 6 into minus 2, that is plus 12 again, then 0 plus 0, that is 1 over 8 to 24, and it is 3. So your gamma RR is actually 3E only, nothing else. There is no contribution from A1 or B1, A2, or I hope that is clear. See, the character table was bigger than before, but it was easy to solve because zeros are, they are more in the reducible representation. Now this is a tetrahedral point group. Your carbon tetrachloride, then CH4 methane, they all belongs to this particular point group. Let us do this RR, and then again we know the formula where AI is sum over R chi of multiplied by chi I. Here your H is how many symmetry operations are there? One identity 8 C3, that is 9, then 3 C2, that is 12, then 6x4, that is 18, and 6 sigma D, that is 24. Total number of operations is 24. So let us see what are you going to get with A of A1. See, here also you can see there are 5 irreducible representation based on the 5 classes. A1 is the totally symmetric one, then A2 is, as you can see, your C3 is the principal axis. With respect to that, it is named as A, and then accordingly to S4, it is depending on that, it is named as plus or minus 1, depending on that it is named 1 or 2. Okay, now it is 1 over 24, 7 into 1 plus 1 into 1 plus minus 1 into 1, then minus, oh, I am doing one mistake. See, I have not taken care of the total number of operation from a particular class. So you have to be very attentive of that. 8 into 1 into 1, then 3 into minus 1 into 1, because all are 1 for A1, and 6 into minus 1 into 1 plus 6 into minus 1 into 1. See how many are there. So this is 1 over 24, then it is 7, then it is 8, minus 3, minus 6, minus 6. So this is actually 0. What about A2? 1 over 24 multiplied by 7 into 1, then 8 into 1 into 1, then 3 into minus 1 into 1, then 6 into minus 1 into minus 1 plus 6 into minus 1 into minus 1. I hope you are following what I am trying to do here. 7 plus 8 minus 3 plus 6 plus 6. That is going to give me 1 over 24 into 15 minus 3 is 12. 12 plus 12 is 24. So that is 1. Okay. This calculation may seems long but very easy, right? So again, E I have to multiply by 2, then 8 into 1 into minus 1 plus 3 into minus 1 into 2, right? Then rest of them there is 0, so I will not write it. It will be 1 over 24 plus 14 minus 8 minus 6, which is again 0, right? What about 81? For 24, that is 7 into 3 actually. Then next I'll not write because it is 0 is there, so I'll ignore that. Then 3 into minus 1 into minus 1, then 6 into minus 1 into 1, then 6 into minus 1 into minus 1. So this is going to give me 1 over 24, 21 plus 3 minus 6 plus 6, that is 24. It will be 1. What about a T2? It is 1 over 24, 7 into 3 again, then 0, then 3 into minus 1 into minus 1, right? Then 6 into minus 1 into minus 1, and here it is actually reverse. It is 1, and it is 1 by 24 into 21 plus 3 plus 6 minus 6. Again, this is same as before. So what we get is that your gamma reducible representation is nothing but 1 time A2 plus 1 T1 and 1 T2. Let me highlight the answer. Okay. With these backgrounds, these are the 4 examples what we have solved today, of how to deconvolute the reducible representation into the irreducible representation. With this, today we will focus on the next part, that is week 8 lecture, that is normal modes of vibration. Firstly, what do we mean by normal? So this normal means actually vibrational modes are orthogonal or independent means we cannot write one of the mode in terms of the others, means they are all obviously they are all orthogonal and they can't be expressed in terms of a linear combination of others. So okay, so how to do this using the symmetry? Obviously we sir has taught you the both the version, that how actually what symmetry is actually doing, how we are for a particular sir has taken an example of a D3H molecule, that is can be carbonate ion or a BF3, so which is D3H, and for different vibrational modes actually you are going to get it through symmetry you have to get the, so your basis here, your I will, before going there, suppose there is a polyatomic molecule like this, which is not linear obviously, but suppose this is a example of a molecule. So what is going to be the basis of, to get the symmetry elements for normal modes of vibration, what is going to be the basis? So your basis is going to be the coordinates of this, coordinate of all the atoms. Okay, so here you have three coordinates, right? Z, Y, X, right? Similarly, these also have Y, Z, X, right? Like this, for suppose you have n number of atoms, right? So your total number of degrees of freedom, or total number of coordinates is going to be 3n, which are independent of each other. Okay, these are all independent of each other. Now in including this, how many are translational? So if we have to focus only on the vibrational modes, so we need to who means we need to subtract the modes of vibration, modes coming from the rotational and translational motions, right? So what are the number of translational modes? Again, so translation cannot be by only one molecule, right? You only one atom. Translation of the overall. So or the translation of center of mass of this molecule. So that has an XYZ. So actually number of translational modes is actually 3, right? XYZ of the center of mass. What about number of rotational modes? That is going to be your, again, center of mass, the rotation along x, rotation along y, rotation along z. So that is 3 for non-linear molecule, but 2 for a linear molecule. Why? Then one of the degree of the freedom is restricted for a linear molecule along the molecular, or you can say that is along the bond, or along the atoms. So that is going to be restricted. So number of rotational modes will be 2 for the linear molecule. So from here we can see, therefore the number of normal modes of vibration is going to be, total is 3n minus 3 minus 3, that is 3n minus 6 for non-linear, and I will write it in a different color maybe. N minus 3 minus 2, that is 3n minus 5 for linear molecule. that is mathematically we know that what are each, right? But what about the symmetry point of view? So for symmetry point of view, your basis set for the mechanism of symmetry operation is going to be the to be all the coordinates, be all the coordinates, 3n number of coordinates. Okay, x1, suppose there is a molecule like this, this, 1 2 3 non-linear molecules of 1 2 3. Okay, so it has xyz, it has xyz, it has xyz. Suppose it has x1 y1 z1. For 2 it is x2 y2 z2. For 3 it is x3 y3 z3. So your basis set will be x1 y1 z1 in a column, only one single column. That is okay, I may denote it and write it once for your benefit. Suppose this is z1, this is x1, this is y1, again this is z2, this is y2, this is x2, then this is z3, this is y3, and this is x3. So your basis set for this particular so if you want to know, so as you can see, this is an C3 symmetry is there, there is an sigma H is there, so this is actually D3H. I'm not particularly saying anything, but it has means I'm not giving you a particular example of a molecule, just a just a quick example. For this you have what are the symmetry elements: D3H, C3 sigma H, this kind of so you need to obviously look at the character table, and character table will be given to you. But for that you have what is the basis function, so you need to uh, find out the transformational matrix for all these symmetry elements related to this point group C3, all how this molecule is going to transform with each symmetry operation. Suppose this one, it will start all x1 y1 z1, x2 y2 z2, x3 y3 z3, and I should write it like this. X1 dash is going to be the transformed axis, right? So we need to find out what is going to be x1 dash, y1 dash, or do you understand what I'm trying to say? X2 dash, y2 dash, z2 dash, x3 dash, y3 dash, z3 dash, and here is your actually your matrix, transformational matrix, that you need to find out, which is going to be here 9 into 9 matrix. Here it is a 9 into 1, sorry, 1 into 9. I always do this mistake, and because due to that you are going to get a 9 into 1 matrix. So your transformational matrix is going to be 9 into 9. It's depend on how many coordinates you are working on or how many molecules you are working on, right? So with that Professor Datta has shown you that how to construct transformational matrix for BF3 molecule, right? D3 belongs to D3H, and he has shown that actually what we are going to see, that whatever molecules has or atoms are going to change their place with the symmetry operation, they are not going to contribute to the character of that transformational matrix or that uh, particular symmetry operation. So I'll write it here. So the atoms which change their position with the symmetry operation will not contribute to the character of the transformational matrix of the symmetry element, symmetry operation. Why? Because they are going to be in off diagonal position. Non-zero parts are going to be on the off symmetry operation. Right. Non-zero matrix elements will be off diagonal. So ultimately you need to focus on the atoms which are not changing their place, so that to and get the character from there. Okay, so we will do that, but we will do with the shortcut method that Shah has shown, but the uh, the understanding is the same. Why we are working with the unmoved atoms? Because they are only going to contribute to the characters, and those atoms which are going to move, they are actually their non-zero matrix elements will be there in the off diagonal position, so they will not contribute to the character. So we will also start with BF3, which is BF3, or let me also write carbonate, right? CO3 minus. So these actually belongs to D3H point group. Okay, both of them. So character table of D3H is being given to you. So we will determine some vibration in three or carbonate, that is D3H point. To do that, what we have to do, that we need to found out uh, that what is the, so we will first draw it. This is B, this is A, this is F, right? This is F1, this is F2, F3, and let me write this as 4. Okay, so here we will write unmoved atoms, that is N, right? So I will just write this over this character table, so I don't have to make much effort. So when identity operation is being performed, then none of the none of the atom change their place, so your 4 atoms will be unmoved. What about when you perform a C3 operation? Then all the fluorines are going to change their place, but boron is not going to change their place. So your unmoved atom is going to be 1. What about C2 dash? C dash 2, that is your along 1BF bond, anyone. So there are 3 C2 dash bonds are there. So if you think about 1, then if you think about the C2 dash along B4 F1, then F3 and F2 are going to change their place. B and F are going to be unmoved, that is your 2 unmoved atoms. What about the molecular plane sigma H? All 4 are going to be unmoved, right? What about S3? S3 is first perform on C3 and then perform your molecular plane. So it is also going to be 1, right? The B is boron atom is going to be unmoved. Whatever sigma V, it is the vertical planes along the BF bonds. So here also 2 atoms are going to be unchanged, right? Okay. Now we have to see that what is the reducible representation or gamma for X, Y, Z. So that means here we will see your XY transformed together with E dash and your Z transformed with A dash 2. They have this kind of symmetry spaces. So your gamma XYZ is actually have is E dash plus A dash 2, that is plus 3 0 minus 1 plus 1 minus 2 plus 1. So I will, for clarity's sake, I will not write the plus. Okay. Now your total number of modes that is n gamma xyz, n multiplied by gamma xyz, or you can also say in other terms gamma 3n is actually, so this is your reducible representation, multiplication of these two, it is 12 into 0 minus 2 4 minus 2 2. So this is our reducible representation. But what about your gamma rotational? So gamma rotational is your Rx Ry transformed together with E double dash and RZ has a A2 dash symmetry, so it is A2 dash plus E double dash, so that is also 3 0 minus 1 minus 1 2 minus 1. So your gamma vibration is actually gamma 3n minus gamma xyz, because xyz is also the total number of rotational modes, right? Then sorry, translational modes, and then rotational modes is going to be, so it is gamma 3n minus this, so 12 minus this, so it is actually 6, then 0 minus 2 minus 2, this is also 0, 4, so this is 4, then this is minus 2, then this is to be 2. Okay. So this is your one of the reducible representation we need to see. This is your total number of, so this will consist, we have to see what are the irreducible representation behind this. So this is your, I will highlight, this is your reducible representation. We need to find deconvolute this. So to deconvolute this, we already know your AI is what we are doing so far, right? Chi of R, chi I of R, right? What is D3H? What is H? Order of the group, 1 identity, 2 C3, 3 C2 dash, then 1 sigma H, 2 S3, and 3 sigma phi, that is total of 12. 12 symmetry operation, order of the group is 12. One way to do this also, to multiply to add the characters of square of the characters of the identity. Anyway, let us see how many times a1 dash is there in this reducible representation. So this is actually your gamma reducible representation. Okay. So now we have found out that what are the number of unmoved atoms, and from there we understood that they are only going to take part in the so they are only going to give you the characters, right? And from them we have subtracted the modes coming from the translation and rotational, and upon deconvoluting that we are going to get the normal modes of vibration. a1 dash, it will be like 1 over h is here 12, then it is 6 into 1, then 0 plus 0, then it is c1h, which is 4 into 1, then it is 2 into minus 2 into 1, then it is 3 into 2 into 1 into 1 over 12, 6 plus 4 minus 2 plus 6, that is 10 plus 4, 14. Did I make any mistake? I think so. Let me check once. 6. Okay, 6 into 1, 4 into 1, then 2 into minus 2 into 1. Okay, I have done a mistake here. See the mistake? This is actually 4. So this is actually going to be 2 times, right? What about no? This is actually going to be 1, right? I should not step jump. Okay. What about a2 dash? That is 1 over 12. Then obviously 6 into 1 plus 0 plus 0 plus 4 into 1 plus 2 into minus 2 into 1 plus 3 into 2 into minus 1. So from here we are going to get actually 6 plus 4 10 minus 4 6 minus 6 0. What about e dash? 1 over 12 6 into 2 plus 0 plus 0 plus 4 into 2 plus 2 into minus 2 into minus 1 and then 0. So this leads to 1 over 12 into 12 plus 8 minus actually plus 4, that is 24, and it will lead to 2. What about a double dash 1? 1 over 12, 6 into 1 plus 0 plus 0 plus 4 into minus 1 plus plus 2 into minus 2 into minus 1 plus 3 into 2 into minus 1. So that is 1 over 12, 6 minus 4 plus 4 minus 6, that is 0. What about a what I will do, I will what I have done, that I have made some space for a 2 double dash, which is going to be a 12 6 into 1 plus 0 plus 0 plus 4 into minus 1 plus 2 into minus 2 into minus 1 plus 3 into 2 into this will lead to 1. But what about a e double dash? That is going to be 1 over 12 6 into 2 plus, anyway there is 0, so I will not take care of this, then 4 into minus 2 plus 2 into minus 2 into plus 1, and again there is 0, so I will not take care of that. So it is 12 minus 8, which is plus 4, and then again minus 4, ultimately 0, so it will not contribute to my irreducible representation. So ultimately what I got is my gamma wave is vibrational consists of 1a1 dash plus 2e double dash, sorry, e1 single dash plus 1a2 double dash. Okay, so these are my symmetry species related to the normal modes of vibration, and total number of vibration, if you check from here, you are going to get 1. Here there are 2 e dash, each e dash has as E dash are two-dimensional irreducible representation, that's why each E dash will give you two modes, and 2 E dash is going to give me 4 modes of vibration, right? Normal modes of vibration. What about A2 dash? It will also give me 1. That means my total number of normal modes of vibrations are going to be 6. So let us calculate from the mathematical expression that is given to us, like 3n minus 6, for this is an non-linear molecule, right? So there are 4 number of molecules, so that is 12 minus 6 is 6, right? So you are also going to get 6 from here, but so from here you are going to get, from mathematically you will say that what are the total number of normal modes of vibration, but you can't say what are the symmetry species each of the vibrations belongs to. So that you can do it from here, that one of the vibrational mode belongs to A1 symmetry, 4 of them have E dash, and one of them is going to be A2 dash symmetry, right? Have going to have. So this is kind of idea you can do, that how to determine this, and we can now go to solve the assignment problems, that is week 8 assignment. But before that, I guess someone is there in possibly there in the, oh my god, the meet is, so I've just rejoined here and share my screen. And let us solve the assignment problems. Okay. So the first question is the point group of IF7 is. So let us first draw what could be the structure. So I obviously being the central atom and F are the pendant atoms. There are 5, so I will, so 5 will be in plane, like a pentagonal thing. My drawing may not, so this is not a this is, by this I am telling you this is the plane, right? 1 2 3, it looks like benzene, which is actually not true, so I will not draw this. This is a pentagonal bipyramidal thing. So these are in plane, and there is going to be one in the top, 2 apes are going to be on the axial positions. So it is actually pentagonal bipyramidal geometry, and by that you are, I guess you have guessed it right, that it is going to be a D5H symmetry. Then the number of C2 axis in CCl4. So CCl4 is, as you know, that it is a tetrahedral molecule, right? So what is going to be the answer? So how many C2 axes are there in CCl4 or a tetrahedral case? I guess you have guessed it correctly. There is 3 C2 axes, but they are not along the bonds. Let me draw it maybe. So one along here, along here, yeah. So can you really going to understand what I'm trying to say? Yes. So your one of the I may draw something else. So your C2 axis, one of the C2 axis is going to go from here. So this is in the middle of this plane and passing through this CCl4. So when you do a C2 operation, your C, let me maybe name it 1 and 2, 3 and 4. Your C is going to be unchanged. 1 will become 2 and 2 will become 1. 3 is going to be at the 4th position and 4th is going to be at the 3rd position. Same along this, same along this. So that's how I guess you are going to get the all the three C3 axes. Okay. So the answer is going to be 3. Now the next question, that the S2 operation on a molecule. So before that, you can always go back to the tetrahedral geometry and see there are 3 number of C2 is possible, right? So from character table also you will get idea how many C2 operations are going to be there, right? Oh, I have not marked it. Okay. So this S2 operation on a molecule with axis of rotation around Z will transform. Suppose what is S2? S2 is first. Suppose there is a sigma H, sigma which will perform later, but first there will be C2, right? And it is operating on XYZ. So XYZ will make it C2 will make C2 obviously C2 along Z, right? So sigma is along XY, right? Specifically mentioned. So C2Z, all X and Y are going to change their means they will have negative and Z will be unchanged, right? But when you apply sigma H, your XY are going along XY, so your XY is going to be same, but your Z is going to change its sign, right? So it is going to be minus X minus Y minus C. Now for Mulliken, for this irreducible representation, you need to denote the Mulliken notation. Suppose E, character of E is 1, that means it is either will have A or B, right? That I will write first, A or B. As the notation, as it is symmetric with respect to the rotational axis or rotational symmetry element operation, it is going to be A. But it is antisymmetric with respect to the next symmetry operation. That is why this is A2, and antisymmetric with respect to center of inversion, then that's why it will be A2U, and antisymmetric with respect to the molecular plane sigma H, that's why it is going to be A2 double dash, A2U double dash. So your second option is correct. Okay. Now let us go to the next question, that is your molecule that has an S6 symmetry element. So your actual answer is going to be SF6. Again you need to see the character tables of this. SF6 is an octahedral. SF6 is going to have an S6 symmetry element. I think in the correct answer, as a correct answer, I guess pH5 is mentioned, but I don't think that is an correct answer. So SF6 is actually correct. Because you will see, do I have a octahedral field? See, the character table of a octahedral molecule, you are going to see S6 symmetry element or operation is there. So octahedral is the correct answer. So again, we need to calculate the normal modes of a vibration of H2O, which is a C2V, right? First and foremost will be calculate using the mathematical form. So there are 3n minus H2 is a non-linear, 3n minus 6, n is 3, so it will be 9 minus 6 is going to be 3. So just check, the first option can give you 3, the second will give you 3 plus 6 9, it is going to be 4a1 plus 5b, that is 4 plus 10 14, and second is going to be also 1 plus 2 3. So you will be confused between first and second if you go by this. So you need to do the shortcut, but a little hard. So this is C2V, H2O molecule, right? HOH. So number of unmoved with identity is 3. C2 along Z is going to be 1, that is oxygen, with sigma V xz is going to be 1, sigma V along YZ is going to be all the 3. Now gamma XYZ is, XYZ have different symmetry species A1, B1 and B2. I will just write it down, 3, 1, 1, 1. Thing call 3 1 1 1. So your gamma 3n or n into gamma xyz is, obviously the point group, order of the point group is 4 anyway. So this is 9 1 1 3. So this, and what about the rotation of the rod? So rotations are also have different species, A2 B1 B2 A1 A2 B1 B2 is 3, then 1, then minus 1. Actually this is also minus 1, this is minus 1, this is also minus 1. So actually your gamma wave actually 6 1 1 3. So how many A1 is there? 1 by 4. Now this is irreducible, we need to deconvolute it. 1 by 4, 6 into 1 plus 1 into 1 plus 1 into 1 plus 3 into 1. 6 plus 1 plus 1 plus 3. I think I have made one mistake. I have to check. Again 3 1 2 sigma b. yes, I have made a mistake here. Because I am adding up A1, B1, B2. That's why B1 is 1, 1 minus this is 1. This is going to be S1. So then your what else? Okay. So I have made this mistake. I have made 6. It should be 3, right? Then minus 1 minus plus 1 0. It should be minus 1. So three minus 1 is still I have made some mistake. 3 minus 1 plus 1 is 3. What is the okay? It will be a plus 1. See, 9 minus 6 will be 3 minus 1. This is minus 2 plus 2. This should be plus 1. Then 1 minus 1 plus 1, 3 minus 1 plus 1, 3. So this is also not minus. So this is actually going to give me 2. What about A2? A2 is 1 over 4. 3 into 1 plus 1 into 1 plus 1 into minus 1 plus 3 into minus 1. So 3 plus 1 4 minus 1 3 minus 3 0. There is no A2. B1 1 over 4 3 into 1 plus 1 into minus 1 plus 1 into plus 1 plus 3 into minus 1. Again it will be 0. What about B2? 1 over 4 3 into 1 plus 1 into minus 1 plus 1 into minus 1 plus 3 into 1, that will lead to 1 over 4 into 3 minus 1 plus 3, that is 4 and 1. So your gamma v is 2a1 plus b2. Here the answer is given 2a1 plus b1. It actually depends that what axis you are taking. If you take your molecular plane as xz, then actually what you are going to do is you are going to get 3 here, 1 here. Then so for this particular case, what I will say that I have taken this as y, this as z, and this as x. But if you take h o h, this as z, this as x, and this as y, then you are going to get gamma v is equal to 2a1 plus b2, because then your n is going to be 3 here, 1 here. So it will be 9 minus 1, 3, 1. Or your gamma v is going to be actually 3, 1, 3, 1. Okay. Then this b1 is going to be here, right? Here. And this is going to be 0 for b2. So that is how one can see this, but anyway you can understand that the last option is not correct. All of these are 2a1 plus b1. Similar thing, the normal modes of vibration for hexachloroplatinate, which has an octahedral symmetry, right? Platinum, chlorine, chlorine, all are in same plane, molecular plane. Now this is Cl on the top and Cl. Octahedral geometry. So by mathematical, how many n's are there? There are 7 n's, right? So how many should be there? 3n minus 6, that is 15, right? So plus, first do it mathematically, then you will see for the first it is showing 9. For the second one it is 1 plus 6 plus 3 plus 6 plus 3, that is, here it is 9 or 12. So 6, 6, 12, 3 plus 3, 6, 18, it is 19, which is not an answer. This is not, this is not. Before going to the vibration, you can try with this can you can do this more quickly, right? If like here both of them have 3, that's why you need to do that. But first check here, 1 plus 2 plus 3 plus 6 plus 3, so 6 plus 6, 12, 6 plus 6, 12 is equal to 15. This could be one of the answer. What about this? 1 plus 4 plus 3 plus 6 plus 3, which is going to be 17, I guess. 5, 3, 8, 8, 10, 9, 17. So only one option with 15. So if you have gone with the rigorous formula, then you need to have time, but here you can save time and you can mark this as the right answer, right? So, but I have given you the character table of octahedral here. Try to perform the, yeah, I have not written it, I will write AI is equal to 1 over H. Try to solve this for hexachloroplatinate, and with this today we will stop our session. I hope this session was beneficial for you, and you have at least got a feeling how to solve this problem, how to get the normal modes of vibration and this kind of problems, and how to obviously deconvolute the reducible representation to the irreducible representation. With in the upcoming week, or maybe in the actually the day after tomorrow, that is Tuesday, we have a session, week 10 session. There we will discuss that which modes of these symmetry species A1 or this are going to be IR active or Raman active. Based on that, we will do that. And with that, today let us end the session. Thank you for watching, and